Welcome back to physics. This will be our first lecture, and we're going to be maintaining the same format like we did in the last cycle. This one, we're going to start off with electrostatics. Key terms for this lecture are electrical force, charge, net charge, conservation of charge, Coulomb, and Coulomb's law. In order to start talking about electrostatics, we have to go back and review some of the material from last cycle. In particular, scalar properties of matter. So now remember what a scalar is. A scalar is something that has a magnitude but no direction attached to it. And so when we talk about matter and the properties of that, what we're usually talking about is answering the question of how much is inside, the amount. The quantities that we're looking at here is the amount. So you can think about it like a jar that you're pouring sand into. How much sand is inside? And so there's three different ones we're going to talk about. Two of them are review, and one is going to be the new one for this lecture. The first is mass. So when we talk about mass, it's the measure. So we're measuring mass, and the symbol we use to measure mass is m, and the units are usually kilograms. They could be grams also. And remember that mass and weight are not the same thing, so a kilogram is not the same thing as a pound. They're two different measures. One is force, the other one's mass. Force is a vector quantity, whereas mass is a scalar quantity. All right, and finally, concepts that are related to mass are inertia and gravity. All right, so that's one of the two that we talked about last cycle. The other one is energy. So the measure is energy, the symbol is E that we typically use, and the SI unit is the joule, and the related concepts are kinetic energy, potential energy, and work. So now, finally, the last thing, and this is what's going to go for the next couple weeks that we're going to be talking about, is charge. Charge is the third property of matter that we're looking at. And so the measure is charge. The symbol we use for charge is Q. And the unit is a coulomb. That's the unit of measure for a charge. And the concept has to do with electricity. Now, these are three separate properties of matter. And so I want to emphasize here, and you should write this down in your notes, that energy does not equal charge. I will say that again. Energy does not equal charge. They are two different fundamental properties of matter. So charge may also have energy, but charge is its own separate thing totally. And we're going to talk about what charge is exactly as we go through this course. To begin to understand this idea of charge, we need to take a look at one of our foundational building blocks of matter, and that is the atom. So in a typical atom, you have three particles that are going around, or two parts in general. You have the nucleus in the center, and you have the electrons which float around outside of it. Now, this is something you should have learned in science classes before about the basic structure of an atom. And there's three particles here that you can see, three distinct particles. And we're going to look at each one of them, and we're going to talk about the charge that's attached to each one. So first, we have Le, the electron. Le is the green particle, and Le is the one that circles around the outside of the atom. So that's these guys right here. 1, 2, 3 electrons orbiting around the outside. And electrons spin around and go around and around because they are negatively charged. So the mass of an electron, as you'll see, is 9.1 times 10 to the minus 31 kilograms. So that's very light. Minus 31 is a hugely small number. So there we go. And our charge is negative 1.6 times 10 to the 19th coulombs. That's also really small, and remember that it's got a negative charge attached to it. Now, for simplicity's sake, when we're dealing with this, because all fundamental particles have the same charge, we're talking about electrons and protons and neutrons and etc., we tend to just use minus 1e or plus 1e when we're talking about charge. So minus 1 charge of an electron. So this e just refers to charge of an electron, which is 1.6 times 10 to the minus 19. So we've got this -1 charge because that's easier to count up the charge, and we can always put in the actual coulombs later. So it's just a different way of representing how much charge there is. Now on to our next particle. We have Paul the proton. All right, Paul the proton is always positively charged. So he always has a charge that is opposite the electron. Now you'll notice here that we have a positive around the charge, but everything else is the same. So we can also simplify that as being +1 e, +1 electron charge. So it's just plus and minus, they're exactly opposite, but there is one big difference between the two that you'll take a look at here, which is that its mass, even though it's still very small, is 10 to the minus 27. So that's a difference between the electron and the proton. So between here and here, that's a difference of 1,000, right? Minus 27 to minus 31. That's a factor of 1,000. So a proton is 1,000 times heavier than an electron. For that reason, because it's heavier, which means it takes more energy to move, which means it's got more momentum, it's harder to change course, we don't tend to talk too much about proton charges as much as we do electrons, because electrons are more lightweight and they're easier to move around and they're easier to kick off of the atom. So if you'll notice here that those protons are attached in the center nucleus and they're pretty tightly bound in there. It's actually hard to break those off. But we can kick off an electron very easily and send it off into different directions. But it's much, much harder to try to kick off a proton. That's actually a lot harder to do. So we tend not to talk about those as much. All right, finally, we have Ned the neutron. All right, Ned, just like his name implies, is neutral. He has no charge at all. So his mass is actually exactly the same as the proton. So he's very, very heavy, but he has no charge at all. And for that reason, we will not be talking about Ned at all in this course. Sorry, Ned, you're just not that interesting. Okay, so we have this atom and we have these three types of particles that are floating around inside. Let's draw a box around our atom. And we're going to totally encapsulate our atom here in this box. And what we want to do is we want to find out what the net charge inside the box is. So net charge, just like we had net force from the last cycle, is the total charge enclosed within a specific area. So I drew this box around, and that gives us this net charge around that area. So let's count them up right here. How many do we have? So we have 1, 2, 3 electrons. So we've got -3e for our number of electron charges. And how many proton charges do we have? Well, let's just count up how many we see here, and let's pretend that that's all that there is. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 proton charges. So we've got 9 proton charges on the inside. And the neutrons don't matter because they have 0 charge, so they don't affect it. So our net charge, that's the total amount enclosed there, is equal to -3 plus +9 gives us a total enclosed charge of +6e, right? Which would be 6 times 1.6 times 10 to the minus 19 coulombs if you want to get the exact amount of charge. So that's how you get the net charge. Now this works, also this idea of net charge works because we have a conservation of charge. Now we talked about 2 other conservation laws before. We talked about conservation of mass and conservation of energy. The combination of those two is what I told you is called the fundamental law of the universe. That is, total charge must remain constant, just like total mass must remain constant and total energy must remain constant. All the same thing. We're expanding our fundamental law of the universe, so now it's matter, energy, and charge can neither be created nor destroyed. That's our new rule. All right, so when we talk about total charge must remain constant, we can also think about it in terms of charge at time 1 must equal charge at time 2. So however much charge is inside of a closed box at a certain time, because it can't be created or destroyed, it has to be there again at a later time. Now, finally, charge cannot disappear or appear from nothing. Again, cannot be created or destroyed. So that's what we mean when we talk about conservation of charge. It has to come from somewhere and it has to go somewhere else. It can't just appear and disappear. So those are all different ways of saying the same thing, conservation of charge. Okay, let's move on then. Now, when we talk about our types of charges, positive and negative charge, their interactions look a little different. And again, this is something you should already be familiar with, but I want to make sure that it's really concrete and that I went over it before we move forward into more complicated things. And that is opposite charges attract. You know this already, you've heard about this. So we have, if we put a positive proton and a negative electron together, they are going to come together and smash into each other. And they're going to get stuck together, just like that. Now, when you look at the atom, you notice that the electrons are orbiting around the proton, which is exactly what happens. Just like a planet is being pulled in, or a moon is being pulled in by gravity and goes around the outside, the electron gets pulled in by the proton, but because it's got that tangential velocity, remember the term tangential velocity, it goes around the outside and starts this orbit. Okay, now, the opposite of this is that like charges repel. So if I place two electrons or two protons next to each other, they'll be forced away from each other. Just like that, quite quickly if they're close together enough, because there's going to be a large force pushing them out. And so that brings us to the conclusion here, which is that this attraction and repulsion is a force. Now remember back from last cycle that Newton's laws govern force. So this is just like any other force, except it is specifically an electrical force. It is caused by charge and not by kinetic energy, not by pushing something physically or mechanically, but by the force of the charge acting on these two objects or these two particles. And that causes them to either attract or get pulled apart. So remember back to your Newton's laws so you remember what a force is, because that's what we're talking about here. Now, Coulomb's law. Coulomb's law, I'm just going to give you the equation right off the bat here so we can see it. And it has to do with determining how strong that force is that's attracting or repelling. So here we go. Force, the electrical force, and now notice here that because charges are Q, I've labeled this FQ here. So the electrical force is equal to K, a constant, times Q1, that's a charge, and Q2, that's another charge, and r squared, which is the distance between them. So let me write that over here on the side. So we're going to have K, which is a constant, which I'm going to give you that number in a second. This is the charge of object 1, and this is the charge of object 2, or particle 2, or whatever you're looking at. So charge 2. And then this down here is simply the distance between them. Okay, now this equation should look kind of familiar to you. I know you're thinking, if you were in this class last cycle, you're thinking, that looks oddly familiar to something else I saw. And you're correct. You have seen something similar to it. And that is calculating out the force of gravity. So this is the formula that we learned last cycle on how you calculate out the force of gravity. And you'll notice that it's very similar. We've got some of the fundamental properties of matter. So over on this side here, we deal with charge. And that's how we figure out electrical force. But on this side here, we deal with mass as a fundamental property of matter. And that determines the amount of gravity. Again, same thing here, distance between them. And we have a constant here that determines how strong the force is. And now G and K are both universal constants. So let's take a look. Let's compare these two forces, our force of gravity and our electrical force, our Coulomb's force. Let's see the difference in how strong these forces are. Now, gravity you feel every day, but you're typically not electrically drawn to different objects every day. So it seems like gravity should be the stronger of the two forces. So let's see how those constants play out, and let's see if that's actually true. So G is 6.67 times 10 to the negative 11th. So that's pretty small, But again, remember that the charges that we're talking about, the amount of charge in each one's pretty small, but we're just talking about the force itself here, so 10 to the minus 11. All right, now what's K? K is going to be 8.99 times 10 to the 9th. Well, it's a lot bigger, a lot bigger. Okay, now, before we move on to actually do the ratio of these two, I want to point out here that the units of this are Newton meter squared per Coulomb squared. Those are the units on this constant K. And that makes sure that when we do this equation that our force actually has the proper units of newtons. Okay, finally, let's take a look at what that ratio is. If I take the ratio of K over G, so the relative strength of those forces, K over G, what's that going to be? Well, here we go. We've got 8.99 times 10 to the 9th over 6.67 times 10 to the minus 11. That is 1.34 times 10 to the 20th, or 134 with a whole lot of zeros after them. 18 zeros here. There are 18 zeros here. 3, 6, 9, 12, 15, 18, yes. All right, and what that number is that is 134 quintillion times stronger than gravity. 134 quintillion times. That's a very powerful force. Hugely powerful, much stronger than gravity. Much stronger. All right. So bear that in mind, that now that we're talking about electricity, we're talking about a really powerful force. Now, here's a question though. Like we said, we experience gravity every day. We're being pulled to the ground by Earth's gravity all of the time. But we're not often pushed or pulled by some electrical charge in a random direction. So, if electrical force is so much stronger than gravity, why don't we feel it every day like we do gravity? Well, there's two reasons for this. Two reasons that we can try to explain. One is that charge can be both positive and negative. So forces are constantly being canceled out and balanced. So I can have, think about in a closed object, that's like our net charge. Our net charge inside of a box often has about the same number of protons as it does electrons. And so the forces tend to cancel out. And since electrons are always being attracted to protons all of the time, they tend to clump together, and then your net charge is zero. So no electrical force is typically close to zero. All right, now compare that with gravity, where there is no opposing force. With it, sometimes if you watch a sci-fi movie or something about future technologies, they might talk about anti-gravity repulsion, or anti-gravity just for short. There is, as far as we know, no such thing as anti-gravity. So we don't have an opposing gravitational force that pushes things away. So gravity only adds. So you end up with this big pull force and no push force. Whereas with charge, you can have both a push and a pull. All right, now that's the one reason. I said there's two. The other reason is that you actually do experience effects of force, but you didn't realize it. And so the way that you experience them, though, you're only experiencing the effects. Now, when you think of electrical force, you think of bolts of lightning flying through the air. But that's often not the case. When we talk about electrical forces, we're also talking about electromagnetic forces. And so this is the force that's responsible for why your body, the atoms in your body, don't fly apart into the universe. Why does an object hold together the way it does and not just fall apart or become gooey and disintegrate? All right, it's also the reason for why right now you're either sitting in a chair or standing on a floor. Why don't you fall through the floor? Now, when I say fall through the floor or fall through the chair, I don't mean like it breaks and you fall down like it's structurally sound, but literally like you phase through the matter, like this picture shows. Why don't you just fall straight through? Well, that's because of this electrical force. This is actually what keeps you from just phasing through material. And if you've ever hit something by accident that was really hard and you hurt your hand when you hit it, right, you can thank this electrical force for it too, because that's what made it feel hard. So you do experience this every day. It's just not that typical bolt of lightning thing that we always think about when we think about electrical forces. So we're going to get more into why this is true, why it keeps your body together, and why it has to do with you not falling through the chair. We'll get into that in class. for now, this is just the basic concept as we're starting to talk about electricity, and we're going to move toward that. This chapter is electrostatics. In a later chapter, we'll move on to electricity, and we'll even build some circuits. Okay, so that's the lecture for tonight. Have a good night, and I'll see you later.
That's all, folks.